start the recording here. Yes, we started this discussion yesterday on the whole question, and we've been doing it in the other course as well, that you're given a transfer function, and the transfer function has a certain time behavior, which is all well and good, and we use the Laplace transform and all that kind of thing to figure that out. But it also has behavior in frequency. And we evaluated that, or we can evaluate that by making a substitution for the transfer function where s is equal to j omega. And then if you have computing power, or you have a lot of time, you can plug various values of omega into that and then plot the magnitude of the response and the phase of the response as well. But what we saw yesterday, and it's typical of the sort of approach that we take in many things in engineering, is that if I can get a model or something that can give me a very, very good approximation of what the real thing is doing, then that gives me enough information that I can see if a design makes sense, if a system is stable, if a frequency response is what I want it to be, without having to get down to the nitty-gritty of building the device or whatever it is. And sometimes without necessarily having to do a very, very complicated analysis. And this way, this particular technique, the Bode plots or Bode plots, came about. And what we do is that we try to look at the behavior of transfer functions in the frequency domain, and we approximate the behavior in terms of straight lines or asymptotes that you know from your maths and mathematics as well. And so, and on top of that, to make things a bit compact, we plot the behavior, the x-axis on a log scale, so that we're able to sort of cramp or compress a fairly wide frequency range into an average page in a diagram. And then we plot the amplitude on another log scale, but this time a log magnitude scale that we use, which is decibels, which is 20 log to the base 10 of whatever the particular value we're looking at. And where we started, and of course transfer functions have poles and zeros, and where we ended yesterday was to confirm something that we knew, that we had introduced from before, that a pole, the frequency response of a pole decreases at the rate of minus 20 decibels per decade, right, throughout its frequency response. And the what do you call it? If you plot a single pole, and where we ended yesterday was to plot a simple pole, which was k over s here, and you convert everything to the log magnitude scale, right? Then you go to k over j omega, right? And then you look at the behavior of that and the magnitude of that, which will give you, when you convert it to decibels, it's 20 log k minus 20 log of omega. And you run that, then you get a straight line, and the slope is the minus 20 dB per decade, right? And the intercept points, of course, the x-axis intercept point is when omega is equal to k. So it intercepts are there. So if you have something like 20 over s, when you're plotting it, it's when omega, this point will therefore be 20, and then it goes backwards and it passes through the point, this point here, when omega is 1, it will pass through at that point, that will be 20 log k. All right? So the other part, so after that now, and then we saw the phase response, that a pole, a simple pole, is 1 over j omega, so that the argument of that 1 over j is minus 90 degrees. So that the phase angle for the pole, right? Did we do that? Right, so the magnitude response was like this, minus 20 dB per decade, and the phase angle was minus 90 degrees all the way through a constant. Okay, so if you have that now, then obviously the opposite of a pole is a 0 at the origin. So what is the magnitude and phase response of that? And of course, at any point in time, feel free to ask or query as well. So the magnitude and phase response, of course, the magnitude of that will be the magnitude of k j omega will be or the magnitude of h j omega in here will be the magnitude, which is k omega, and the angle is 90 degrees. And you plot that 20 log k plus 20 log omega. So as you would expect, the zero is the mirror image of the pole. So whereas the pole decreased at minus 20 dB per decade as the frequency went up, the zero is going to increase at plus 20 dB per decade as the frequency goes up. Yeah. And again, you can think about it as like the voltage across a capacitor. When the frequency is very low, the capacitor, a capacitor is essentially an open circuit, so anything passing through it will be very small. And as the frequency goes up, it starts the impedance drops, the reactance drops, so it conducts more and more, so that the amplitude of any signal passing through it will start to rise. Okay, so that's the sort of behavior that you see here with a zero. The pole, of course, is the reverse. So depending on where the reactive elements are in circuits, you either have the frequency increasing or the frequency decreasing. Right? So that's fairly straightforward. And of course, the zero is the opposite of the pole. So the angle is plus 90 degrees. And what about multiple poles? So s squared, s cubed, and so on, or I should say maybe 1 over s squared, 1 over s cubed, and the like. And we met that in the course of doing all our discussion on active filters. And we expect that every time, so n equal to n equal to 1, we have minus 90 degrees as a phase shift. And it decreases at minus 20 dB per decade. Right? S squared will decrease at minus 40, as we proved with the second order filters this morning. And the phase angle now will be minus 90 by 2, which is minus 180. And so you keep going on. Right? So the slopes, as you say, n goes 1, 2, 3, and so on, they all pass through this point here. Right? Because that's the point where omega will be equal to k, so log of where omega will be equal is 1, so log of 1 is 0. So they all will pass through that point, but the slope will vary in multiples of 20 dB per decade, depending on what the order of the particular transfer function is. Right? And of course, the phase angle will change in multiples of 90 degrees, or multiples of pi over 2 radians. So n equal to 1 is minus 90, n equal to minus 180, n equal to 3 minus 270, and so you keep going on. Yeah? And the zeros, of course, so we can move through this one fairly quickly. The zeros are, of course, a mirror image. So the zeros, and it's easy reading, the zeros, of course, increase, they all pass through the same point here, and they increase at multiples of 20 dB per decade, and as you go along. So already you could see, even from this side now, which is into the transfer function itself, that if I have a transfer function and the transfer function has a certain number of zeros, the zeros are going to make the frequency response to that go up, and poles are going to make the frequency response go down. So combinations of poles and zeros can give me all sorts of shapes of the frequency response, like the low pass and the band pass and the high pass responses and so on, which is why we were making the point when we were designing them in electronics, that you watch, when you're looking at the thing, like a simple low pass has one pole, a high pass has a pole and a zero, and you'll see that the location of that is what creates the behavior, and so you go on. Right? So the poles and zeros, which was a point made back then, the poles and zeros determine the frequency response of a transfer function. Yeah? And of course, the angles for the poles, the angles go positive, plus 90, and so you go on. So that's basic stuff. The real fun now starts when we have the more common transfer function. So like this thing, a single pole transfer function where the pole is not at the origin. So we met this kind of behavior before. This is the transfer function, and just to connect the two classes, this is the transfer function of a low-pass filter. Remember we did that, right? And instead of, we had it as omega over S plus omega C, right? If you remember that from yesterday, and we touched on it this morning. So what's the magnitude and phase response of a transfer function looking like this without plotting it one radian at a time? So of course, the first thing is that to go from the transfer function to the frequency transfer function, we make the substitution S equal j omega. So the transfer function now becomes P over j omega plus P. And then for the purposes of plotting the straight line or the Bode plot, we have to express it in this form, and you'll see why in a second. So we always try to get the transfer function into this form or in a form k over 1 plus the poles, right? Poles, right? And we'll see the multiples of that going around. So you try it, and we'll do the same thing for the zeros, 1 plus the zeros, etc., all the way through. So we get it in this form, and that is fairly easy. You just swap them around, and then you divide the whole thing through by P. Right? Nothing too extraordinary. And this is where now we use this behavior to plot what the thing is going to look like. So let's look at the behavior of h of j omega at the extreme values of omega. Remember, we're plotting this, so we want to take omega from low, which is essentially 0 hertz, up to some reasonably high frequency. We don't know what that is as yet. So the first thing is that if omega over p is much less than 1, in other words, this is another way of saying if omega is much less than p, right? So if omega is much less than p, then this fraction here is going to be less than 1, right? In other words, at the point where omega is much less than p, so whatever frequency p is, if omega is much less than that, this transfer function, as far as frequency concerned, basically is 1 over 1. And you convert that to dB, you get 20 log of 1, which is 0. Right? So omega much less than p, the frequency response of this is close to 0. So if I were to draw it on a frequency diagram here, this is dB here, this is omega here in log, right? P is somewhere along the place, right? P is some point here. This is P. If omega is much less than P, then the, what do you call it? The transfer function basically in decibels is at 0. Yeah? Make sense? Right? No argument with that, right? And then we now go to the other one. If omega is much bigger than P now, so if omega is much bigger than P, in other words, omega over P is much greater than 1. The transfer function, the lower part of the, if you convert everything to dB, the transfer function is 20, remember we're dealing with, where are we? 1 over 1 plus j omega over P, right? So convert that to dB, I have 20 log 1 on top minus 20 log, well, 1 minus the 20 log, oh, that's very bad writing, but anyway, omega over P, right? This is 1. This is supposed to be a G here, right? So Log of 1 is 0. So we don't care about those things. But what basically is happening is that the transfer function, as omega gets very bigger, the transfer function essentially in decibels behaves as minus 20 log of omega now. Right? Minus 20 log of omega is a line that is decreasing at minus 20 dB per decade. We went through that. That's a first order pole right there. Yeah. So if I put everything now on a straight line graph, this is P here, right? So this is omega equal to P. That point is P. When omega is less than P, is 0 dB. And when omega is much greater than P, it's a straight line descending at minus 20 dB per decade. And what we do, because it's a straight line or an asymptotic plot, we just draw the two straight lines and notice that they intersect at P. So in other words, the straight line approximation of P over S plus P, when you convert that to the frequency response domain, which is 1 over 1 plus j omega over P, you get a behavior that is looking like this, right? Which is the low pass filter response that we know already. Yeah, fair enough? Everybody following? Let me know if you're not, okay? Are we following? Yeah? All good. Okay, the class rep said all good. Good. There we go. Right, and let's look a little bit about what happens at this point here. Right at the point where our straight lines, we are drawing it like this. So that's our approximation here. But let's see what happens at omega equal to P. At the point where omega is equal to P, the actual value of the transfer function is this. If omega is equal to P, then we're dealing with 20 log of 1 over root 2. That is this bit inside of here, which is minus 3 dB. That famous minus 3 dB thing that we kept talking about. So in fact, the true response is going to curve a little bit. The true response does that. The straight line response is a red line. So our error at the intercept point is minus 3 dB. But we accept that for our purposes, we didn't have to do any big setup plotting. We already have an indication that if I were given a P over S plus P type transfer function, that is a low pass filter transfer function. It is going to change at some frequency P, and this is what the response is going to look like. Right? Low pass, so it is flat up until that frequency, and we call that frequency the corner frequency, the break frequency, the cutoff frequency. You're going to see all sorts of terms for it. We kind of just randomly use the word corner frequency anyway. All right? And the decrease, because it's a single order system, is going to decrease at minus 20 dB per decade. Right, that's a magnitude plot. Remember, we also have a phase plot to deal with. So what about the behavior of that with respect to frequency? When omega is much less than P, this essentially, if omega is much less than P, then this part cancels out. So the tan of that will be the imaginary over the real, which is 0. So there's no 0 degrees. Right? When omega is much greater than P, then we have a situation where we have the inverse tan of something approaching infinity now. Of course, it's 1 over that because the j is on the bottom. So it approaches when omega is much greater than P, the phase angle approaches 90, minus 90. And then at omega equal to P, of course, we have 1 over 1 plus j. And the argument of that is, of course, minus 45 degrees. So the phase behavior of that looks like this. For omega much less than P, the phase angle is 0 degrees. For omega much greater than p, the phase angle is minus 90. And we're doing straight line approximation, so it's going up until the corner frequency, and then it changes to minus 90. We know that that isn't true, and we could calculate it, and we know in fact that what will happen is going to pass through minus 45. That's the point when omega is equal to p. It actually passes through minus 45, but it changes somewhat gradually between the two extremes. And we met that when we did a first order filter plot yesterday afternoon. All right, so the magnitude plot, kind of superimpose it here. If you were to put a magnitude plot here on the same frequency, then while the phase is doing that, the magnitude does this up until p, and then decreasing at minus 20 dB per decade. Right? Yeah? No, maybe? Make sense? Right? Sensible. Okay. We'll go with that. So the other one, of course, is a transfer function looking like this, which is a single zero transfer function. This should be a p here. Little typographical error here. So this should be p. All right? So transfer function s plus p over p. What is the magnitude and phase of that? Of course, well, we make the substitution s equal to j omega, and we express it now in the form of 1 plus j omega over p. All right, so all the zeros we express in that form, all the poles we will express in the form 1 over 1 plus j omega over p. Right? So zeros are like this, and the standard form for the poles are like that. Right? So same behavior here. And if you look, when omega is much less than p, for instance, close to 0, the magnitude is 20 log of 1, which will be on 0 dB. When it is much greater than p, the omega over p part, this dominates. Right? So the response becomes a normal 0, which will increase at 20 dB per decade. And so you have that, we went through that. Okay, so it's going to give you this now, which is the opposite of the single pole transfer function. And of course, the phase now will, if you were to plot the phase, right, as you would expect, the phase now will be 0 up until the corner frequency. But because it is a single zero transfer function, the phase is going to go to plus 90 at the corner frequency. All right, so it's the reflection, the zero function is the reflection of the pole. The frequency response of the zero is the reflection of the pole as well. Right? Nothing in that. Nothing too difficult here. Right? And the phase, well, we just saw that the phase angle will do the same thing, and it passes through. So the straight line phase plot is the orange straight lines that we have. The asymptotes are that, but you understand that in reality that the transition, it really passes through 45 degrees, and it's slowly increasing, or gradually increasing, or changing, I should say, from 0 to 90, but through the 45-degree point. So at this point, what will happen is that you're in a position that if you were to be given a transfer function, a magnitude and phase transfer function, that the magnitude looks like that, and the phase looks like that, right? Which is, this is minus 90, and this is some frequency, let's say 100 radians per second, right? You could watch that, and this is 0 here. You could watch that and say, okay, this is a simple single pole, because this is minus 20, let's say, you can watch that and say, okay, that's a simple pole transfer function, and that therefore is 100 over s plus 100. Yeah. So you could go back and forth now. Given this straight line plot, you could get a transfer function. Given the transfer function, you could get a straight line of what the frequency response would look like. And that is usually enough for in a design case to let you know if you're on the right track or not. Because if you had a transfer function, let's say you get some transfer function, we haven't gotten it, we get a little more complex in a little while, but you get some transfer function, and instead of doing this, the transfer function may be doing you this. Then you already know without doing anything else that something is wrong with the transfer function, right? And all you would have done is just to draw it by a straight line. Fair enough? Which is what the whole process is about. So now that we know that, the next step, of course, is to sweeten the pot, add some more seasoning, as they would like to say. So let's add now. So we have this one, right? This was the one that we just did. So immediately you could see, okay, this is a single pole transfer function. And now you could watch this, draw the axis here, and tell me, okay, the corner frequency is 10. At 10, so this transfer function is going to go from flat here and decrease at minus 20 dB per decade. And here's 10. And that the phase is going to go from 0, and then at 10 is going to go to minus 90 degrees. Right? So we could do that now just by inspection. Right? So this is just review here. Right? And this is how you do it if you want to check it, and you have this, you have this on your slide. That Matlab, and I've been using this when we do the filter design very regularly for you all. So you set up, basically you set up two arrays of the coefficients, the numerator and the denominator coefficient. Matlab has a command TF that creates a transfer function. So it will create a transfer function object H. And then if you tell it to use the same command BODE, common letters, it is going to plot the frequency response, but it's not going to plot a straight line one. It's going to calculate and plot the actual response for you. So this is a good way to check sometimes. If you have the thing, if you want to check that to see if your straight line approximation is good. So our straight line approximation for this would have been just what we just did, that. And our straight line approximation for the phase would have been that. Yeah? Good enough to go. We have an error of minus 3 dB here, that we just showed. Here the error is a little bit bigger, but we understand what's happening. It's going to start at 0 and it's going to land up at minus 90 degrees. So it's going to transition fairly gradually from 0 to minus 90, right? And the higher the order filters, is the quicker that's going to happen, which is what we're coming to. Yeah, so you can always check, like for homework or anything else, or when you're even revising the filter stuff on the next side, that you could use these simple few lines of Matlab code, and you can get a frequency response plot that will quickly indicate if you whatever you're doing is correct or not. So let's throw in some gain, right? So the transfer function now is, by the time we have it, so here's a transfer function, and the original transfer function therefore would have been something like, let's say, where am I? Put this here, k over some arbitrary transfer function, or k over s plus p. So the substitute here, of course, is s equal to j omega. So the next step is k over j omega plus p. And then the next step is to express it in the standard form. So you're going to have to divide through by p so that you get k over P over 1 plus j omega over P, right? And then, of course, they convert everything to decibels. So in our case, this thing K over P is A here. So nothing strange going to happen there. You take logs of everything as you did before. And if you do that, what is going to happen here, when you take when omega is much less than P, right? Omega is much less than P, so this essentially falls out. So what we have is 20 log A minus 20 log of 1, which is 0. So that omega much less than P, the straight line is going to be at whatever 20 log A is going to be. And then when omega is much greater than P, this is the corner frequency. From that point on, when you reach frequency P, is going to decrease at minus 20 dB per decade, whatever A happens to be. Okay, so if you plot it, right, then this is the main difference here, that they know the flat line wouldn't be at 0 dB, but it will be at 20 log A, the low frequency asymptote, as they call it. So like, for instance, if we were to do a transfer function like this, right? So if I give you this and I tell you, okay, as a little exercise, look at that Bode plot and tell me what is the transfer function that made that. Okay, so the transfer function, first thing, you need to get what is the corner frequency, right? Because why you get the corner frequency? Because that tells you where the transfer function is something over something plus P, or whatever the corner frequency happens to be. It's easy to find the corner frequency. You look at this and you check first off, this is decreasing at minus 20 per decade, right? So we know it's a first order. If it's a first order, the frequency response does this, the phase response, and it passes through minus 45. We know where minus 45 is. We could see it on the graph that we just had here. I'll get rid of my own scratchings. If you look at that point right here, you can see that on a log scale. So this is 10, this is 20, this is 30, that is 40. Right? So the corner frequency is 40 radians per second. Look at this point. That is 5. That is 5 dB. Oops, write it properly. 5 dB. Right? So 20 log of A, 20 log A is equal to 5 dB. Right? So you can solve for what A is, therefore. So once you know that, then the transfer function now, HS, whatever made that, is A over S plus 40. Yeah? Easy? Yeah, no, maybe. Right. So you can watch the diagram and you can work backwards, or you can watch the transfer function and get the diagram. That's the whole idea behind this. You can go back and forth. So let's add a little more seasoning as we keep going along. So what about this kind of transfer function now? Here we have 1, 0, and we have a quadratic down at the bottom. So what is the magnitude versus frequency response? How fast is going to fall off? What is the phase now? So here we go. We're starting to get more realistic in terms of what the behavior looks like. The first thing you do with a transfer function like this is to see, once you're given a quadratic or you're given any sort of polynomial below, can this factorize? Right? Because if it can factorize easily, and I mean factorize meaning simple poles, right? Simple poles, and I'll put in brackets or zeros. So can it factorize if I have simple poles or zeros? So you can look on this and see if this can factorize, or if not, 10 and 4 will give me 40 and will also give me 14. So just by inspection, this one is fairly straightforward. So the first step is to try to see if I can factorize this thing, right? Of course, if it can't factorize by inspection, you can use a quadratic formula and get the roots. If the roots turn out to be complex, we have a part that we're going to deal with on that. So you factorize it. That's step one. Step two now, of course, we make the substitution s equal to j omega so that we get it into the Fourier, or get the frequency or the Fourier transfer function. And then the next step now is to convert this into the form 1 plus something. So you need to do that in a couple of steps. You look at the numerator, so the j omega and the j omega plus 4, right, is 1 plus j omega over 4, right? But you have to have a 4 on the outside if I break it up into that. Then the other one is 1 plus j omega over 10. We're going to have a 10 outside that. So multiply by 10, and then we have 40 j omega. So if I convert this into the standard form, I'm going to get j omega over 1 plus j omega over 4 plus 1 plus j omega over 10. Yeah? Make some sense? Right, just do the arithmetic carefully. This is very simple algebra. So we're looking at this thing now, and we have 1, 0, and 2 poles. And we start to plot now. You get a piece of paper, and you draw how the thing is behaving in terms of each of these components here. So the good thing now, the next step is to draw the magnitude, which is to convert everything to dB. And the great thing about logs is that when you convert this entire thing to dB, it's going to be 20 log of this, minus 20 log of this, minus 20 log of that. Or if you flip it over, 20 log of this, plus the minus log of that, plus the minus log of that, etc. Right? So you basically add up each response. So this is a simple, the numerator is a simple 0. So I can start sketching it. You look at the thing now, and first off, we have a simple 0. So a simple 0 is going to pass through, you remember where? It passes through omega equal to something on the x-axis. When omega is equal to something, it crosses the omega axis. This is supposed to pass through the point 1. Right? So it's going to pass through the point 1. Then this one, what's the corner frequency for that? Omega equal to? Don't all rush. What's the corner frequency for that? A lot of hard mathematics here. Corner frequency for that is 4. And the corner frequency for that is 10. So let's put all of the 3 plots now together. The 0 increases at plus 20 dB per decade. The first pole does this until it reaches 4 and decreases at minus 20 dB per decade. And the second pole does this and decreases at the same minus 20 dB per decade. Make your lines equal, parallel, all right? Make them, it doesn't have to be just a sketch you're doing, but try to make the slopes look equal, right? Where they have the same slopes. So you plot all 3 of them, and then you do the cumulative now. So here we have it. No, the corner frequencies at omega equal to 4 and omega equal to 10, not minus 4 and minus 10. right? It's an actual frequency, omega equal to 4. You're not solving the equation, it's where the corner frequency, where it is going to, to change, all right? So at that point in time now, we have, this is the 0 here. This is the first one. And then the second component. And we add them up now because it's all logs, so we're adding up the responses. So if I add it up cumulatively now, right, and I'll draw it in black. For omega less than 1, and it should be right here. So sorry. For omega less than 1, what are the three components I have? I have 0 plus 0 plus the minus 20 plus the plus 20 dB per decade for the 0, right? So that this line here, the sum of all three responses up to here is a line like that. Between 1 and 4, we have the 0 increasing at 20 dB per decade. And we have the two other transfer functions still at 0. Yeah? So the net response is that it's still going to keep increasing at 20 dB per decade. Between 4 and 10, I have plus 20 going up here. This one is decreasing at minus 20. And the other one here is still at 0 dB in that little zone. So plus 20 minus 20 plus 0 means that the response between these 2 points is going to flatten out. No dB, no change. And then as we go beyond the 10, we still have the plus 20 here. This one now kicks in, so you have minus 20, and we have minus 20 here continuing. So plus 20, minus 20, minus 20 is going to give me a total of minus 20. So in other words, the frequency response for that particular transfer function is going to, a straight line response is going to look something like this, right? Kind of like a bandpass filter in a way, yeah? Everybody following that? If you're not, now is the time to ask the questions. You take the transfer function and you break it up into each of its components. So each of the components, as we went back here, each of these components, right? So you have the transfer function, the 0, one simple pole, one simple pole. The corner frequency for the 0, a simple 0 like that, that passes through 1 radian per second, and it's increasing all the time at 20 dB per decade. The corner frequency for this, we wrote it that way so you know what the corner frequency is just by inspection. So the corner frequency for that is 4 radian per second. The corner frequency for this component is 10 radian per second. So once you do that, the rest is really to remember what the responses of these things are. The zeros increase, the two poles, they're simple poles, so they're going to decrease at minus 20 dB per decade as once you pass the corner frequency. Before the corner frequency is flat at 0, after the corner frequency decreases at the straight line, decreases at minus 20 dB per decade. And once you remember that, you put everybody together on a map, and then you, on the diagram, as I say, try to keep the lines with similar slopes. Try to keep them at least parallel to each other. If you happen to be drawing it on an existing scale, that's fine. But if you're sketching, it's just an image that you're trying to create. So to avoid confusion, because if both of these supposed to be at 20 dB per decade, but you draw one like this and you draw one like this, you're going to get some strange, a strange looking diagram coming up. So you try to keep the lines with similar slopes looking the same. And then you just add it up. Each frequency you have. So you have 1, you have 4, you have 10. So you're going to see what are the three lines doing before 1? What are the three lines doing before 1 and 4? What are the three lines doing between 4 and 10? And what are the three components or the three lines doing once you get past 10? And you draw a straight line for the performance in each of them, and that is your asymptotic plot for that particular transfer function. Yeah? And you could check it, as I said, you run this stuff through Matlab if you like, and Matlab is giving me the red line, or a straight line approximation with a black. The Matlab is giving me the red line. So this is good enough to go. The black line is more than enough to tell me if that particular transfer function made sense or not. Yeah? And what about the phase? So this is only half the black is your straight line. Black is not the reference CD. Black is our straight line approximation, right? So black is what we get. Right? Good. Black is what you get when we take, remember our three components. We were given, forget the black line. When we did the three components, we had three things that we created using our knowledge of the frequency behavior of the transfer functions. So we drew the red straight line here on the page. We drew the blue response, and we drew the purple response. The black is when you add all three of them together, because the transfer function is composed of all three. So how the Bode plot works, we plot them one at a time, and then you add up all three. Yeah? So Joshua, what you were saying about the slope? Joshua, you were asking something about the slope. I didn't quite catch what you were asking. Right, okay, because the 20 dB, the plus or the minus 20 dB per decade had to do with what we started the class looking at. That a simple zero, the frequency response of a zero, it passes through omega equal to 1, and the slope is plus 20 dB per decade. And the poles, in this case, this pole at the corner frequency, which is 10 for this one, below 10, when omega is much less than 10, the transfer function is essentially just 1. So log of 1 is 0. And when it is much greater than 10, the transfer function is basically omega over 10, which is a pole that decreases at minus 20 dB per decade. And then we do one line for this, one line for this, one line for that, and then we add up all the three lines, and we come up with the black line is our straight line approximation. And just to show what the reality is, the red line is what the real magnitude plot would have looked like if you went and plotted all the frequencies. So as you can see, our straight line approximation is more than adequate to let us know what for instance, if I were designing this and I wanted it as a bandpass filter, right, just for argument's sake, this is enough to let me know, right, okay, the behavior is what I want. Nice. And that's all I need to know. The black went to 0 between omega and, right, yes, because the 0 was increasing at plus 20. The pole at omega equal to 4 was decreasing at minus 20, and the other pole that had the corner frequency at omega equal to 10 was still at 0. So plus 20 plus 0, or sorry, plus 20 minus 0 minus 20 will give me a flat 0 dB per decade. So it flatlines basically between that point. Yeah. And what about a phase? There's only half the answer. You have to look at the phase, and the phase plot is just as straightforward. The 0, you remember, the 0 is a constant. A 0 is a constant plus 90 degrees, right? What they call it, the first pole goes until the corner frequency, it goes at 0, and then it decreases to minus 90. So you're on the same diagram just below the magnitude to make sure you have the same corner frequencies here. The 0 is at 90 all the time, plus 90. The first or part of the transfer function with the corner frequency at omega, it goes to, for less than omega, it's at 0, and then it changes to minus 90. And then the one where the corner frequency is 10 is 0 degrees up until 10, and then it also changes to minus 90. And you add up everybody again. So between 0 and 4 radians per second, it's plus 90, right? Plus 0, which is plus 90, right? Then between 4 and 10, it's plus 90 for the 0, it's 0 for this one, and it's minus 90 for the other component. So that's 0. So it goes to 0 here. And then beyond 10, it's plus 90, minus 90 for the first component, and minus another 90 for the second component, which means that is plus 90, minus 90, minus 90. So it's going to land up at minus 90, which is the overall black line here. So this is what my phase plot looks like. Right? The cumulative phase plot, it's 0, then it goes, sorry, it's plus 90, then it goes to 0, then it goes to minus 90. All right, so it's changing the idea that I want to get from this as a designer, or whatever it is, that the phase starts at plus 90 and it lands up at minus 90. All right, if you want to draw the true thing, of course, you plot it, and this is what the plot would look like, that blue line there. But this should be enough to let me know that the phase is going from plus 90 to minus 90 for whatever sort of design I had in mind. Yeah? And of course, you could work backwards, therefore, given a phase plot and given a magnitude plot, you could kind of try to piece together what the transfer function may look like. But the idea is that having a transfer function, and you don't have Matlab or you don't have a calculator available to you, you could sit down with a piece of paper and a transfer function, and you could sketch out what the magnitude and phase plot looks like. And that is what Bode had in mind when he came up with this. Yeah. So, and here's one that you could try on your own time when you're reviewing the notes after you did that. Try this one and see what sort of response you're going to get for it. Yeah. So let's take a little break here, and then when we come back now, we look at a little more complicated situation and see where we go from there. All right. So I'll stop the recording.